Hey guys, so I'm going to give you a video here, less than 10 minutes, I promise. You can use this to do I think you have 4 problems due tomorrow. I will post that right after I do this. So we've talked about concentration changes, we've talked about temperature changes. So now pressure changes is a little more complicated. Now, this only for gases too, only for gases. So I already pre-wrote this here so to save time. So, equilibrium shifts towards smaller number of moles if pressure is increased, and the equilibrium shifts towards greater number of moles if pressure is decreased. So that's I don't know why I wrote that like that, but those are the rules. And this is only for gases. Pressure really only affects gases. So what this means is when you have an equilibrium, a chemical equilibrium, a reaction at equilibrium in some sort of sealed container, and you increase the pressure on the entire container, or you decrease the pressure on the entire container, the reaction will change which direction it favors. So that's a term I haven't really used too much in AP Chem. That's way more common. That when we say it shifts towards a smaller number of moles, that means it favors that direction. And then if it shifts towards the greater number of moles, it favors that direction. So when you have a container or a flask, wherever these reactions are occurring, if you change the pressure on the entire container, these are the rules. So let me give you a couple examples here, and then you'll do your assignment, and then we'll go over this again tomorrow. And I do have in those YouTube videos the animation. There is one on pressure and gases, but I'm going to show you that tomorrow. So here we go. I'm going to bring this up. All right. So first thing, actually, I have to mention here is if you have a reaction where there's no difference in number of moles. So let me go back up here. So again, the smaller number of moles, greater number of moles. What that means, so I guess let me explain that first. What that means is if you have a reaction, and I like to use this one, 2H2 plus O2 yields 2H2O. And these are all gases. Gas, gas, gas. Okay, I have 2 moles. So let's say, here, you know what? Let's do this. Here's a container. All right, and I'm going to kind of just do this. This represents that. Okay, so there's like your dividing line between reactions and products. It doesn't work this way, but let's just do it this way to help you understand. I have 2 particles of hydrogen, right? So here's my 2 hydrogens. 2 moles, that's really 2 moles, but for the sake of this, let's say 2 particles. Oxygen, here, we'll do oxygen in blue. So oxygen is going to be here, okay? Now over here, I have 2H2O2, right? So I have 2 oxygens here and then 4 hydrogens. All right, the Mickey Mouse. Okay, all right. So as you can see, I have 3 moles of reactants and I have 2 moles of product. Again, I'm just drawing 2 particles, but really this means 2 moles, which is really 6.022 times 10 to the 23rd particles times 2. We don't need to get into all that. The point is I have less on the product side, more on the reactant side. So this is fully capable of being balanced, right? Balanced reactants here, products here at equilibrium. So we're going to the right, we're going to the left at the same exact time. The rate of the forward equals the rate of the reverse. These are occurring simultaneously. So you don't have to have the same number of particles on both sides to be at equilibrium. I've said that a lot. They just have to be changing back and forth at the same rate, meaning the number of reactants and the number of products stay constant. So I always have 3, I always have 2. If one goes over here, one goes over there. It isn't about how many particles you have. And yes, we use the analogy of weight, but again, that's just analogy. Okay, so hopefully all of this is making some kind of sense. So what I just wrote above this, the notes here, is that if you increase, so let's say this is our container, and we increase the pressure in here. How could we do that? Well, we could shrink the container, right? We can make the container smaller, so if there's less space, there's more collisions, increasing the pressure. So the notes and the rules state if we increase the pressure on this container, what's going to happen is it's going to shift to the right. If we increase the pressure, it will shift to the right. And then the opposite is true. If we decrease pressure, it'll shift to the left. It's very hard to show that here. I understand that. So let me actually erase those. Okay. So let's explain why. So if we increase the pressure, we're going to make more water and we're going to use these two up. The best way to kind of teach this, it's really hard to use the seesaw analogy. So here we go. And this is more I don't care about that. The way I explain this is just kind of out loud. So, I'm running out of battery. That's why it got dark. All right, I got to do this quick. All right, so if I increase the pressure on this entire container, think of this little box as the reactant area, and this little box is the product area. If I shrink this container, thereby increasing the pressure, my reactants have less space than my products. So less space means they feel the pressure more than the products. Since the reactants have more moles, there's less space. They don't like that. They feel crowded. So some of them react and go over to the product side to alleviate that pressure of the crowdedness, right? So that's my way of explaining. If we increase the pressure on this whole thing, the reactants actually feel it more than the products. So they react and they shift to the right, making more products. If this was in reverse and I had more products, if I had more products and I increased the pressure, then the same rule would apply, but we'd go to the left, right? So it always goes from high moles to low. Pressure goes from high to low. The opposite concept is a little more confusing. If we decrease the pressure, so make this box bigger, now what happens is the side with the lower number of moles, it's almost like, the side with the higher number of moles, if we decrease the pressure, so we make this area larger, so here's how I say it. They like the spacing they have originally at equilibrium. If you make this too large, there's too much space. They want their pressure to go back to being where it was. Well, the only way to do that is to introduce more particles to take up that extra space. So if I decrease this pressure, meaning making this area larger, now some of these are going to come over here. Products will break down, make reactants to kind of fill in the extra space, right? So essentially the room is too big and they want more people, more particles to fill in that space because I just decreased the pressure. So if I decrease the pressure, it wants to shift towards the higher moles to go back to being the pressure it was at equilibrium. I know that's confusing, okay? I only gave you a few problems here, and I'll talk more about this tomorrow. And again, so just let me summarize. If I increase the pressure on all of this, the higher number of moles feel too crowded. That's too much pressure. They don't want that much, so they get rid of some particles to go back to being at the pressure they were. And then if I decrease the pressure, there's too much space, not enough pressure, so particles move into that area to go back to the pressure they were at equilibrium. So again, that's my explanation. Hopefully it made some kind of sense. And if you want to just try and memorize this, the definitions here, then that's fine as well. But you know my thing with I want you to understand it, not just memorize. So I'm going to stop the video. Use this to do the work due tomorrow. I'll see you guys tomorrow.